we have been utilizing a lot of the work out of ISRQI. And I'm really excited to demonstrate what we've been doing with it and how we've been using it to connect these condensed matter systems, especially in the way that that you guys might be familiar with these UDW detectors. So in essence, I wanted to show you that, and the way I wanted to show you that is that these condensed matter systems can be thought of in the realm of conformal field theories. So these applications that I'm going to be demonstrating and that Michael showed you the experimental form of them, we realize the UDW detector model through these conformal field theories. So again, just a quick motivation. I'll show you this cartoon slide that basically demonstrates some of the systems that Michael showed, where we had the bulk system. You can imagine that the bulk system had the where he showed the bulk system, and then these left and right moving edge states were the very white borders, and then we had these cadmium telluride Q dots that were placed around the outside. And we can turn on and off the interaction by lowering the potential well that was created with that top gate that Michael said. And this demonstrates also the scalability of this program, where we can scale up the system by just adding more of these systems on top of each other. And that's and one feature of this was the all-to-all connectivity. And we can demonstrate how this all-to-all connectivity can be scaled up in some very, again, most of my talk will be idealized up until the very end, when we start to recognize, as Rick said, where some of the real world issues start to come into play. But the idealized system, where we open up the potential well on two sides and create a bulk between the systems, such that these topological edge states only exist on the boundary, but they do so between both the systems. And now if you see that if we take detectors like C and B, there's a direct communication in figure D there, as opposed to in figure C, where the C and B are in order to communicate, they'd have to utilize A as an intermediary. But this is sort of like the cartoon model of what Michael was telling about with this topological edge states and the cadmium telluride quantum dots. So in essence, we want to recognize the UDW quantum computer Hamiltonian. So we've been calling this, affectionately, the Unruh-DeWitt quantum computer. And in essence, the reason being is we wanted to, in order to realize this connection, we wanted to realize these spin qubits connected with quantum fields. And it turns out that that's kind of a common thing in condensed matter literature, and it's known as the Kondo impurities. So probably many of you are familiar with the Kondo impurities. And we can write down some sort of interaction Hamiltonian that links the Kondo impurities as a spin qubit. And that's just connected through some coupling J to some Dirac fermion current, right? With left and right movers given by the pluses and minuses, right? These Kondo qubits can then, they take the nice form that when you apply some sort of like external magnetic field to the system, that it really shows up as a two-level spin structure system, where we have a true, Unruh-DeWitt detector with two levels, different energy scales with a coupling. And we'll talk a little bit at the end about some, realities with this coupling. But for now, let's stick with the idealized model. And there's some issues with this literature. I mean, ISRQI, you guys are you are fully aware of a lot of issues that are going on here. Fermions are hard, right? And there's been some perturbative treatments with fermions, but in general, we're not interested in perturbative treatments. We're interested in strong coupling. That's going to be a very key takeaway from this, is the strong coupling. And fermions are just really complicated. But we have a little bit of promise. We have lots of room to work with. If you look at equation 5, we have the full fermionic Luttinger liquid Hamiltonian. And in this, there's several blocks of different physical systems that we can utilize. And as I'll show you, some of these blocks of this Hamiltonian, especially this J3 block, will really come into play and really do a lot of work for us here. But this full Luttinger liquid Hamiltonian is very common in the literature. Like I said, a lot of this stuff is very well understood. But in order to do it, we really want to bring it in the UDW model that you guys have been working on so hard and have done a lot of good work with in the past decade and a half or 2 decades or so. And so those of you who aren't familiar, we just have this Unruh-DeWitt detector. It's a 2-state system coupled to a quantum field. And the coupling is really, it's it fully relies on the switching function and the smearing function, and this is what allows the spin moment and scalar field to couple together through some coupling constant that I've labeled J, which is not the traditional lambda for the community, but it is in the condensed matter system. So, and then we have a goal, and here's the goal, and that is if we have two detectors like these cadmium telluride Q dots, and we want them to communicate through this field, then we're going to have to set up a system like this. We're going to want to utilize quantum Shannon theory because this is the theory of quantum communication, and these qubits are gonna communicate through the quantum field, and we're going to effectively measure the coherent information currently. If there's time, I'll talk a little bit about how we're going to extend that into something a little bit more rigorous than coherent information. But in essence, we can measure the coherent information, and then I get to your guys' work at ISRQI and all the excellent work you guys have been doing. So here we have this is the work that's done by Pitar, Ida, Akim, and Eduardo. And what they showed was that if you have a unitary gate that looks like this with one of these field operators, it looks like a controlled unitary, right? And you can set up this structure so that it really models this interaction here, or these unitary couplings here. And this unitary is, it's pretty easy to set up. You can just set it up with a single scalar field and a single UDW model. But unfortunately, this single controlled unitary results in a loss of quantum information because in essence, you're really like spreading the entanglement out between the fields and the qubits. So this isn't going to work. But what Pitar and everybody found out was that you can actually introduce a second controlled unitary gate. And this second unitary gate has some very strict restraints put on it. But when you show those restraints, you get to write down this nice quantum channel here. So I really want to point out, and this is going to be one of the really important parts of this talk, is that these field observables, these 8 vertex operator looking like field observables show up in this correlation function in the quantum channel because the field is traced out. And that's an important fact because these have really natural extensions in conformal field theories, right? Like these are just 8 vertex operators that are we're worried about the correlation function of 8 vertex operators, which shows up a lot in different conformal field theories. So, ultimately, let's not get into the other aspects of that, but regardless, we have, if we want to pay attention to the field's role in this field-mediated communication, it really exists at the level of this correlator, okay? So, what we want to do, so we're going to choose a Gaussian smearing function, and what we really want to do is measure the coherent information if we have a quantum channel that looks like, equation 11, and with the correct constraints in place, and to see all these constraints, you can look at either Pitar's paper from 2019 or 2020, and my paper from that we put out in September. Both of those will be in the end of the talk. Those are where we go into very rigorous details about all of the constraints that you put on the model. And when you do, Pitar found this really nice, in one dimension, this really nice plot where he plotted coherent information to channel capacity. And as you can see, as the coupling strength over the smearing function, that fraction gets larger. The channel capacity, which is a measure of communications between the qubits, reaches the prime objective of 1, where it becomes perfect communication. So this was really exciting for me to read. I really think this paper by Pitar and all will be a really big it'll be really big one day when people start to realize the importance of these models for quantum transduction, for quantum communication. I think that this work is going to be really important. So let's revisit our fermion model. What can we do with this work, right? This work is not, this work has been around. What can we do with it? And it turns out that we can take our Hamiltonian with the Kondo impurity and the Luttinger liquid. We'll still look at that electron block, or the electron current block of the Hamiltonian. We'll set it up and we get a unitary. If we set it up with the UDW model, we get a unitary that looks like this, where we have in equation 14 where our observable O is some fermionic observable, but it's a quadratic coupling. Quadratic couplings are hard. You need a quadratic coupling with fermions because you need to preserve the number density, or the fermionic density. And so we just have this model that's just difficult to work with because it's fermions. But we, really quick, conformal field theories in general, they're going to play a big role. There's lots of conformal field theories that have equivalent in condensed matter systems. If not the system itself, then different analogies like the Kutayev-Honeycomb model, Ising model, the SYK model. All of these utilize conformal field theories. So this measure of field observable correlators is really going to be determined, the usefulness of this field observable correlators is going to be determined by how well we understand those correlators in these CFTs. Ours, we're doing the Luttinger liquid, and the conformal symmetry provides a straightforward mapping between the fermions and scalar bosons, and this is where things become really fun. So if you're unfamiliar with bosonization, it's just a straight mapping of fermions to bosons. And the thing that's interesting about this model, about this mapping, is that at the level of the correlators, there's an equivalence. The equivalence is that, at the level of the correlators, the fermions are identical to the scalar bosons, which is exciting. Because that means we can take our difficult fermion model, we can bosonize it. I got to go a little bit faster because I don't want to go too much over time. And what we can show is that if we want to recover the same channel capacity that Pitar et al. Were able to find, then we want to take we want to bosonize our system. Oh, I do have to show you one other thing. If we look at equation 23 here, we have our original gate model with our two fermionic operators, and we bosonize it, and now we're down to a single scalar field, which, if you recall, did not preserve entanglement. If you wanted to use it as like a quantum state transfer channel, it did not use that field to transfer the entanglement. Instead, what it ended up doing was spreading the entanglement out. But if we look at that full J3 term of the Hamiltonian, we have both the current density and the current, the electron density and the electron current, this rho and J here, right? We plug them into our model. Now, this is a bit of a toy model and a bit of an idealization, sure. But we plug them into our model, and what do we find? We find equation 26, which has the exact same structure that Pitar was able to produce with his scalar fields. And subsequently, we were able to produce the same type of graph that showed that this channel that was produced, again, let me remind you, produced by quantum dots coupled to these fermionic fields, okay? Through this helical Luttinger liquid, these topological edge states, that we were able to produce the exact same gates that Pitar showed at the limit of infinite coupling, resulted in perfect channel capacity. There's a lot more to this full Luttinger liquid model, right? Each one of these bosonization processes has a different system that you could look at. Each block of the Hamiltonian is a different physical system. Each bosonized form or fermionic form provides a different channel that would be interesting and have different quantum information properties. These are not easy. These cosines and these sines have been absolutely destroying me as far as trying to find these quantum information calculations. But these are things that we have to consider. I mean, look at the interaction type. The third one down, we have backscattering. Backscattering is a real issue in these systems physically. And to understand the bosonic form and the channel that would show up from the type of operators that come from this is something that really does need to be evaluated at some level. But what can we do with this? I mean, there's not just experimental progress in this. We can actually talk about theoretical progress in quantum Shannon theory applications, right? One thing that we did, and we put the paper out in September, is that we actually showed that instead of wrapping all of that switching and smearing function in the coupling constant, if instead you model it as just another parameter, what does it look like? And it turns out that it looks just like a dephasing parameter, because really the goal is if you wanted these coherent states to be orthogonal. Okay, and that's one of the restrictions we talk about a lot is these orthogonal coherent states. Because coherent states are famously non-orthogonal, right? So these restrictions in place force that orthogonality. Then if you wrap up all of that switching and smearing functions into a parameter, it looks a lot like a dephasing parameter that kills the off diagonals in the mixed out density matrix that is the coherent state density matrix, right? And so here in equation 32 and 33 is really the recognition that we're taking the coupling constant and the field, the smearing of the field, and we're recasting it as some dephasing like parameter, okay? And what do we get? Well, we can actually add extra detectors that make noise to the system. We can use this letter B as a ratio of the coupling to our wanted detectors versus unwanted detectors. And what we can find is we can actually model this noise really simply without having to add a significant amount of vertex operators to this correlation function. Because of course, nobody wants to do that integral. Nobody wants to integrate over 12, 16 vertex operators. So instead, having a dephasing like parameter and then modeling this like it's a bosonic dephasing channel, which of course it's not, but it looks like one in the most traditional sense of bosonic dephasing, which is just destroying these off diagonals. We can actually model this noise with these detectors as, with coherent information very straightforwardly. And we see that in some cases, if the coupling to some detectors, we notice that you can actually increase the coherent information for a short period of time at these different energy scales. But nevertheless, it's just, I think the takeaway was that, different viewpoints give us different models or different, it can make the calculations a little bit more feasible, right? So I'm running out of time. I guess my conclusions are, where are we at? And here comes the reality of the problem, right? The theory, we have a UDW model with Kondo and Luttinger liquids. These are all well established. The experiments, well-known TMDs and quantum Hall effects, as Michael showed you. But, we're not interested in this, and we're not interested in this. We're interested in this, right? Quantum transduction in quantum materials. That's the goal. And with it comes a lot of issues. You have the Kondo problem, the RG flow. You have the Hilbert space dimensions because there's no such thing as infinite coupling strength. You have self-interacting and backscattering parts. You have bulk interactions, time evolution. I mean, the list goes on and on of these things that are going to be real considerations that we have to look at. So to do that, we need a lot of time. We need a lot of collaborators, people who have done with this stuff. But ultimately, the goal in this is that the quantum transduction gives us a first look at fermionic flying qubits, right? That's an exciting aspect of this, right? Those Dirac fermions in the topological edge states are actually carrying the quantum information. So we have a first look at fermionic flying qubits. Another thing is these thermalization in quantum materials is a topic that people are very interested in the condensed matter community. And these things, they might not be industry standard, but some of these have direct analogies to what Rick was talking about with superconducting qubits and transduction. That's a very important concept right now in industry. And I think that models like this, that we can actually realize this transduction in electronic systems and fermionic systems, might actually shed some light on those more industrialized systems as well. So with that, I thank you. And here are some references if you're interested in looking on more.
Amazing. Thank you so much, Eric. Thanks a lot for this talk. This was truly interesting.